Thanks for joining, everyone. It's a pleasure today to welcome one of my former co-authors, maybe a future co-author again at some point. Josh Coombs from the University of Colorado, Boulder. And Josh is going to tell us about some work that he's done with some of our other Australian friends on bosonic codes. So please take it away, Josh.
Yeah, so thanks for having me. And I think both Anna and Ben are in the Zoom audience, so this will be interesting. At the end of the talk, or maybe Ben can post it, Ben's given a similar talk on this, which is much more technical than the talk that I'm going to give today. So if you want further details, you can check out Ben's talk on YouTube. So I think in this talk, I'm going to focus on introducing bosonic codes for about a third of the talk. And this is because they're, I'd say, pretty unfamiliar to most people. And then the middle third of the talk, I'm going to talk about this joint work with Anna and Ben, who are at Sydney University and RMIT University. And this was recently published in PRX, and it's about bosonic codes that have a rotation symmetry. And the figure you can see here in the middle of the screen is a state that has an n=3 discrete rotation symmetry. And this is actually a plus x eigenstate for one of these rotation symmetric codes. And then I think at the end of the talk, if we have time, I will discuss things, well, future questions and areas where perhaps people in the audience can try and contribute to this field. There's a lot to be done because it's a pretty unexplored area. Yeah, okay, so I guess the other thing I should say is that some fraction of these slides have been stolen from Ben, and oh, why is that not progressing? Okay, there we go. So for universal quantum computation, it's pretty clear that Hilbert space is one of the primary resources. And this is because if you have a very small Hilbert space, it's easy to simulate these things. And this is true even in the presence of noise, perhaps more so because we need to use Hilbert space to encode our quantum information into an error correcting code to protect against the noise. And so there's many approaches to this. There's error suppression techniques, but at least within error correction, there's two approaches that have become pretty standard. The first one is to take a bunch of finite dimensional systems and take your quantum information and spread it out over those finite dimensional systems. And you use an error correcting code to do this, and the excess Hilbert space that you have left over from encoding is then used to detect and correct the errors. An alternative approach is to consider a system that has an infinite dimensional Hilbert space to start with, or at least a very large one, and then encode your information into that. And a really good example of this from first year quantum mechanics is the harmonic oscillator. So in this figure here, you can see the harmonic oscillator, and these dashed lines here are the energy eigenstates and some associated wave functions. And so there's two fairly convenient ways to think about the harmonic oscillator. First is about in this energy eigenbasis where you have a discrete spectrum, but it's still infinite, it's countably infinite. An alternative approach is to think about the operators and states on this harmonic oscillator in terms of things like the position and momentum operator, which have a continuous spectrum. And so you can construct states and operators by taking superpositions or mixtures of the eigenstates of, say, the position operator. So the important thing to note is that it doesn't matter which way you construct your error correcting code, you have to answer a number of questions which are listed down here. And these are the questions of like, how do I encode it? How do I manipulate my information? And finally, how do I correct the errors? And probably most importantly is this number 5, which is at the end of it, once we've finished encoding and decoding and correcting, did we actually gain anything from performing error correction? And so we're going to, the middle part of the talk is going to be stepping through these points 1 through 5 in gory detail for the case of a bosonic code that has a rotation symmetry in phase space. Okay, so there's many ways you could encode information into a harmonic oscillator or into a bosonic mode. And conceptually, the simplest way to think about this is picking 2 orthogonal wave functions or approximately orthogonal wave functions, and then they form a 2-dimensional subspace of the larger Hilbert space. And one that is going to be useful later for comparing the more exotic things is what we call the trivial encoding. And so in the trivial encoding, you take the vacuum and the first excited state of the harmonic oscillator and encode your information into these 2 levels here. Now, this is a perfectly valid error correcting code. It's not necessarily a good one, but it's probably better to think of this as just a physical or raw encoding of the information. Right. So once you have these 2 sort of orthogonal states that define your code space, you, this is your bosonic code over here. You need to protect your information against well, you're hoping that the code will protect your information against the typical errors in these bosonic systems. And those typical errors are loss, heating, and dephasing. So loss should be pretty familiar to everyone. If you think about something like a pendulum or a mechanical oscillator where friction will, for example, cause energy relaxation and eventually stop the motion. And this is the same kind of error as loss in the bosonic context. And then contact with a hot bath, that's heating. And then dephasing is kind of like a mixture of rotations in phase space. So these are the 3 very natural and dominant errors in bosonic systems. So you're hoping that whatever code that you design will be able to correct these errors. And normally we think about say qubit codes discretizing the continuous errors that we get. It's slightly different, and we'll get into those details in the next section. But there is some discrete. Why is it going backwards now? There we are. There is some discretization errors, and what people, discretization of the errors, and what people are imagining doing, at least initially, is concatenating these continuous variable codes with qubit codes, and hoping that that would be part of a larger system where you could hope to prove fault tolerance. This is not necessarily the best way to go. I'd say one of the big lessons we learned in the early 2000s in the error correction literature is that concatenating codes is not a good idea. It's better to design a code from scratch on a larger system. But this is what people are mostly doing. Okay, so any questions so far? Nope, okay. So I said that the simplest way to think about codes in this really large Hilbert space is you just pick 2 states that are orthogonal or approximately orthogonal, and then this forms your error correcting code. The problem with this is that there's no guarantee that these states that you picked will have obvious or simple to perform logical gates, and it's not clear that the error correction or the syndrome measurements will be easy to perform. So one possibility is to step back and look at codes in terms of, or at least look at phase space and codes in terms of discrete symmetries. Oh, I've got to use that again. And broadly speaking, there's 2 classes of discrete symmetries, well, 2 classes of codes that have 2 kinds of discrete symmetries. One is a translation symmetry in phase space, and another one is rotation symmetry in phase space. So if we take the harmonic oscillator and look at the position wave function, so this is an inner product of some general quantum state with a position eigenstate. For the translation symmetric codes, you have these superposition of position eigenstates that have some sort of spacing between this lattice. And this superposition of like this Dirac comb goes from -infinity to +infinity. And then we call this the 0 state. And then the 1 state is simply you take the 0 state and translate it by half of this lattice spacing. And then these two states are orthogonal. And for the dual basis code words, for the X basis code words, it's actually easiest to think about those in the momentum representation, but and in which case they look identical to 0 and 1, plus and minus look identical to 0 and 1, except the lattice spacing is different. But to be consistent, we will stay in the position basis, and things are also kind of obvious there if you think about, oh, that's right. These are called GKP codes, these translation symmetric codes. And that's after the after Gottesman-Kitaev-Preskill, who did this paper. Wow, it's almost 19 years ago. So the plus state, of course, is just the equal superposition of 0 and 1. And then the minus state is, of course, you get a minus sign on the 1. And the periodicity you can see here in the position eigenstate, in the plus and minus eigenstates, is sort of doubled compared to the 0 and 1 code words. And the structure of these codes has already told you roughly how the operations work in this. In the position representation, we can see that we just have to displace 0 to 1. And then if I was to show you the momentum, I said that it looks very similar. So again, it's going to be a displacement to take you between plus and minus. So for the rotation symmetric codes, there's a very similar story. Now we're looking at the energy eigenbasis, or the Fock basis, for a harmonic oscillator. And it starts at 0 and goes up to infinity. And I've just chosen a spacing between the amplitudes on the 0 code word. And in this case, it's 8. There's 8 Fock states between them. And 1 is, I simply take 0 and I translate it by half the number of Fock states. So I've translated it by 4, and those two states are very clearly orthogonal. And then there's a similar story for the plus and minus states. Now we have an equal superposition of 0 and 1. And so you can just see if I add the green and the red, that I get this sort of orange. And now this has a spacing of 4. So this is actually going to be what we call a code that has an n equals 4 symmetry. And the minus states have simply just the plus state with a minus sign on every other amplitude. And so these in both of these codes, the code words, the amplitudes go out to plus and minus infinity in the translation symmetric, and they go from 0 to plus infinity for the rotation symmetric codes. Any questions on that? Okay. So unfortunately, those wave functions are not normalizable. So we make approximate codes, and the way we do that is by putting a cutoff somehow on the wave function. So you can see here in the translation symmetric codes, what people typically do is they put a Gaussian envelope on top of these this train of delta functions, and this causes the translation symmetric codes to actually lose their translation symmetry, or their perfect translation symmetry. And in the rotation symmetric case, you can see that one way to do it is you put an envelope on top of your coefficients in the Fock basis, or simply you can just cut off the coefficients in the Fock basis. And one of the consequences of these is that this inherent noise associated with these codes, which don't show up in qubit codes, for example. Right. So here are some Wigner functions for people that like to look at them. So this is a full representation of the quantum state. And the translation symmetric codes, you can see have this sort of Gaussian envelope where they're dying off in all directions. And this figure is taken from this paper by Victor Albert. It's a really nice review on the area from a few years ago, but the area is changing so much that it's already missing a few references. And then over here in the rotation-symmetric codes, you can see that this is an n=4 code. You can see there's a rotation symmetry in these x basis code words. This is the plus state, this is the minus state. And then the Z code words have an 8-fold rotation symmetry. And I think that they just look very impressive, but yeah. So the reason why this whole area is, well, at least in this section, I want to tell you why everyone is excited about this area. And I think perhaps maybe some reasons why you might be convinced to work on this area. So I think the first reason is it's not just one hardware platform. So traditionally, for many qubit platforms, you typically have something like this down the bottom here. You have a 2-level atom coupled to some harmonic oscillator, and you either use the harmonic oscillator to read out the state of the 2-level atom or to help perform operations on the 2-level atom. And in these bosonic codes, the role of these two systems is reversed. You are now using your harmonic oscillator to store your quantum information, and then you're using your 2-level atom typically to manipulate your information. So in circuit QED, it looks something like this. You would have like an LC oscillator, and this is your harmonic oscillator. And then you have a nonlinear inductor with a capacitor. So this is an anharmonic oscillator. And this is what you approximate to be a qubit or 2-level atom. And so now we're using this object here to control the states and operators on this linear system over here. And say for ion traps, you're interested in using the internal degrees of freedom of the ion to control the motional degrees of freedom of the ion. There's also work in progress in optical systems. It's quite challenging there. There's, I would hope that perhaps one of the groups puts out an experimental paper in the next couple of years, but it could be a while. But the point here is that there's many systems that this applies to. Another reason why we're excited is that these codes have already achieved what's called break-even, and this has not yet been achieved by any qubit code, even the simple repetition code. So let me explain what that is. So if we just go back to here, remember there's essentially two systems. There's a 2-level atom and some sort of harmonic oscillator. In this comparison here, we've got the green line here, which is the 2-level atom. And we can see that we're plotting the process fidelity as a function of time. And we see that the longer and longer we leave the 2-level atom, the worse and worse the information is degraded, or the channel becomes worse and worse. And then we do this trivial encoding that I mentioned earlier. So we take the 2-level atom, we transfer the information from the 2-level atom into the cavity. This is encoding, and we're encoding it into the 0 and 1 of the vacuum and first excited state of the cavity. And you can see in that encoding operation, you've already taken a little bit of a hit in the channel fidelity here, the difference between these green lines. And that's just generically true for encoding. But then otherwise, you can see that the cavity is much higher quality than the harmonic oscillator is much higher quality than the artificial atom. And so its channel fidelity is staying higher for a lot longer. So now we do the additional thing, which is we take our information, and instead of encoding it into the ground state and first excited state of the harmonic oscillator, we encode it into a Cat code. And so this is one of these error correcting codes that has a rotation symmetry. And we do some number of rounds. So we do a round of error correction and detection. And we see that actually the fidelity is a little bit worse than this raw encoding, but the longer and longer we leave it, we're starting to see that we're achieving parity with the raw encoding. So that means all of these additional operations of measuring syndromes and applying a feedback operation, a correction, and then decoding has actually given us performance which is comparable to this uncorrected Fock encoding, or this encoding. So this is called break-even. Then the additional step is if you now post-select on a trivial syndrome, this means that you're either getting a no error or a logical error. And when you do that, you see that the channel fidelity increases. So this is very impressive. It's never been demonstrated in qubit error correcting codes, but it's been demonstrated in multiple bosonic codes that have a rotation symmetry. So the other one is this paper here from last year, which is binomial codes. It's a very similar story. The black dots here are the artificial atom. The blue is the raw harmonic oscillator encode, the 0-1 encoding of the harmonic oscillator. And then the green is the encoding into the binomial code and the correction. So this is pretty cool. Another reason why we're excited about these bosonic codes is that they're believed to be hardware efficient. So I think a few weeks ago you had Tom Stace speaking in this seminar, and he and Anna and Dat and Clements have been thinking about, in the context of superconducting qubits, very small circuits that have as their ground states code words for an error correcting code. And so we're sort of hoping that we can build things that are error correcting codes with small amounts of hardware. And that's another reason why we're excited. The second reason is that we can build qubits that are sort of naturally robust, or qubits that have bias noise. And here are two examples. There's a few actually. These are both from experimental papers. I've chosen not to show the data, but they're basically implementing the same idea, and one is doing it using Hamiltonian evolution, this one here, and one is doing it using dissipative evolution. But the essential idea is you create, say in the Hamiltonian case, you have this parametrically pumped Kerr-nonlinear oscillator. This is something that Jared Milburn and Kathy Holmes studied way back when, and they showed that there was a degenerate ground space, and subsequent work realized that you could use this to encode quantum information. And so here you see that you have this sort of, these two steady states of this phase space. In the dissipative case, you use two photon dissipation using this as the argument to the Lindblad superoperator. And this again causes you to have these sort of steady states here. And the cool thing about this is that the experiments showed that they suppressed, in this particular encoding, they suppressed bit flips exponentially. And so this means that at a higher level, if you were to concatenate this with a qubit code, you would have highly biased noise, and this could be very useful for you know, bootstrapping to get better thresholds and so on. The final reason is that there's a real possibility that we could make the error correcting codes autonomous. We could make hardware that makes the entire error correction procedure autonomous. And this started, this kind of idea started a long time ago with Mohan Saravar and Jared Milburn. But more recently, there's been optical implementations suggested by Hideo Mabuchi's group, where they imagine there's a bunch of atoms in cavities and a bunch of controllers. And in this particular circuit here, you just turn on two lasers and it automatically implements the bit flip code. And they've generalized this to Shor-Bacon codes too. So this can do, they have this for a full quantum error correcting code. Unfortunately, in the optical domain, we're limited by the nonlinearities that we have. And so in the superconducting realm, there's these really nice proposals by Elliott Capet, where he takes a small number of nonlinear elements and shows that you can have a circuit that autonomously does error correction. Of course, this means that there's assumptions about the noise and the recovery that are baked into this circuit. Okay, so I think that's the end of my pitch on why you should, well, why I'm excited about these bosonic codes, and sort of going to move into a bit more of the technical stuff now. Is there any questions on the first part? Okay. So in the rotation-symmetric codes, above all else, we hold the discrete rotation operator sacred. And in particular, we define the code words of the rotation-symmetric code to be the +1 eigenstates of this Rn operator here. So it's indexed by this integer n, which specifies the level of symmetry. So if n equals 2, then you have a twofold rotation symmetry. And so this is very much like a stabilizer in qubit codes. And we can give you an explicit way to construct a code. And we start with what we call a primitive. And so here I've taken a blob, which is meant to represent, say, a coherent state. The displacement from the origin is the mean of the coherent state. And then you have the 1 sigma ellipse. And you take it and you superpose it with rotated versions of itself. And this forms the 0 code word. And you can see that even though this has an n equals 2 symmetry, the 0 code word actually has an n equals 4. It looks like it has an n equals 4 symmetry. The 1 state is very similar, except every other one of these superposed states has a minus sign in front of it. And this guarantees that 0 and 1 are orthogonal. Now, the dual basis code words are a little bit trickier. So now you have to take a superposition of 0 and 1, and this will give you the plus state. And you can see just by looking at the colors here that the red and green are going to cancel. And so this will give you this blue state here. This is the plus code word for an n equals 2 code. And this one you can actually see has a n equals 2 rotation symmetry. If I rotate it by pi, it will be back to the same state. However, if to construct the minus code word, I now subtract the 1, and this gives me a cancellation in a different way. And this is the minus code word here. And the cool thing is you can actually see here that if I rotate by pi on 2, that I've actually transformed my plus state into my minus state. And this is so actually this rotation by pi on n is the z operator for our code. The other thing to note is that if I rotate the 0 code word or the 1 code word by any amount, I'm never going to transform 0 into 1 or 1 into 0. And that's because the rotation is never going to affect the phases between the lobes of the superposition.
Josh?
Yeah.
When you were talking about rotating this plus into the minus,
yeah.
That's missing a minus sign still, right? But do you just then rotate and then allow it to delay?
You pick up the minus. So, I mean, what will happen is basically the, oh, sorry, maybe I don't understand. You're saying that
So you've got, okay, maybe.
Like,
oh, okay, sorry. So I thought there was I thought there was a global phase there, but that's not. It's not. It's okay.
not. Yeah, yeah. No, it's kind of magic. It just works.
Yeah. Okay.
Well, it's not magic. Yeah, it's designed to work this way.
Sure. Okay. Sorry,
yeah.
I misunderstood. Thanks.
No. I mean, I got confused myself. So, okay. The thing that this primitive state lets you do is essentially by choosing a different primitive state, you can choose, well, you can design different codes, and these codes might be better for different channels. So as an example, here we've got the cat codes, which are essentially, so these are n=4 codes, and the red are the plus states and the blue are meant to indicate the minus states. So up here, it's like a cartoon picture. I've not, here's the proper Wigner function here, and you can see that there's all these crazy interference fringes. So in these sort of ball and stick diagrams, I'm really just representing the classical parts of the wave function. And so here, we're basically taking a coherent state and rotating and superposing it with itself. You can imagine squeezing that coherent state, so then you would have a squeezed cat code. And then there's these other codes which were proposed in this PRX paper down here by Michael et al. And these are called binomial codes. They're known to be very performant. And then finally, you could take, for example, just the equal superposition of the Fock states and superpose that with itself. And we call this a Peg-Barnett code, which is related to the eigenstates of the Peg-Barnett operator, which is the Hermitian phase operator on a truncated Fock-space. So one of the things that happens when you impose a discrete rotation symmetry is that actually imposes structure in the Fock basis. So here you can see that if we have a rotation symmetry of 2, then we actually see that the Z basis code words have a spacing of 2n. So in this case, it's 4. And what the primitive does is the primitive tells you the amplitude of these different coefficients. Well, the weight and the phase of these different coefficients. Now, I guess the other thing to point out here is that you can see that if you had, if we start looking forward towards error correction, if you had a loss event, and let's naively model that as just every state in the harmonic oscillator ladder gets lowered by 1, then for this n=2 code, if I could measure photon number perfectly, then I could still distinguish the logical 0, an error occurring on a logical 0 and an error occurring on a logical 1. So this leads us to thinking about how to measure our encoded qubit. And it's actually pretty simple. So the Z basis, the measurements are just photon counting. And if there's been no error, all you need to do is check whether you're on this green grid or this red grid. And so you can think of this as just checking the photon number mod some number. Of course, you'd want to do this destructively, so you'd need to do couple this to some ancillary system and measure that system. But to do an X basis measurement, it's a little bit trickier. Actually, what you need to do is distinguish between, say, in the n=2 case, these two states here. And one way to do that would be to perform this thing called a phase measurement. And this is a technically challenging thing to do, but it has been done experimentally. And the problem with these phase measurements is there's no Hermitian operator that corresponds to a phase operator, to phase. And that means, but however, there is a generalized measurement, so a POVM. And that means that there's no eigenstates of phase, so that means you'll never have a perfect phase measurement. So there's always this inherent phase error or embedded phase error that's really determined by the primitive that you use. So there's the next thing to talk about is how do we manipulate this quantum information? And we've already seen that the rotation by pi on the pi on n is the z gate. So if you use the projector of the code space projector, you can take this operator, project it into the code space, and see that it is in fact the logical z operator. And so it will have these relations down here if you apply them to the 0 code words. And we saw that the z operator actually flipped the x basis code words as it should. The tricky one is actually what's the x operator, and it turns out to be this horrendous thing here, which is doing exactly what we said earlier. It's taking the 0 state and shifting it up by 1, or shifting it up by n. So this was an n equals 2 code, so it's shifting this state up by 2. And again, if you take the projector onto the code space, you can figure out that this is indeed logical logical x. The problem with that is this is only approximately true, and that's because unless you have one of these codes that has flat coefficients in Fock-space, then translating the 0 state up here up to 2, you will also have to reweight the amplitude, and this is only going to be possible to do. Well, it's very difficult to do, so we're going to try and avoid doing that when we talk about our logical manipulations. The final thing to mention is the number phase trade-off. And so you can see here that if we increase the spacing between 0 and 1, that we can increase the resilience to loss events or increase the resilience to heating events. The problem is that as you increase that spacing, it means that the spacing in phase space here becomes smaller and smaller. So this is an n equals 4 code here. I've depicted this is the plus code word, and this is the minus code word. And on the previous slide, this was an n equals 2. So on this one here, roughly you could think that if I wanted to bin these two, I could draw a line at, what is that, pi on 4. And if I saw a rotation error where I was rotating up from the plus state towards pi on 4, then I might apply a correction back down to the plus state, for example. But you can see in this code here, we're going to have to look at an angle like pi on 8 to make that sort of decision. So as we increase our resilience to loss errors, we're decreasing our resilience to rotation errors. And so there's this number phase trade-off that which is sort of characterized by this relationship here. Yeah. So initially, when we were trying to cook up error correcting schemes, we were thinking of doing pretty wild things like trying to measure the z basis errors and then apply a correction, and then try to measure the x basis errors and apply a correction. And it was really hairy, and mostly because the x operator is very unphysical. And at some point, Anna realized that there was a really nice way to do this that avoided all of it. And that's what I'm going to explain now. So first of all, for universal quantum computation, we use this weird gate set, which is we prepare plus states. We do x basis measurement, which is going to be our phase measurement, S gates, CZ, and then to get universality, we need to inject a T state. And there's various easy gates that come from the fact that our code has rotation symmetry, but probably the one to highlight is what we call the C-rot gate. And it's a rotation-controlled rotation, and the physical implementation is via a cross-Kerr nonlinearity. And the cool thing about this particular gate is that it can interface code, two different codes. So as an example, you could do a logical CZ gate between between one qubit, which is in a n=2 cat code, and another qubit, which is in a n=7 binomial code. So this is pretty cool, and I think it's a great feature of these kinds of codes. And we said that you'll notice in this universal gate set, we don't have an X gate. And so actually a lot of our gates, although they could be implemented with unitaries, we implement via teleportation, but I'll probably skip over that. So with continuous variable error correction, the syndromes are often richer than the sort of binary syndromes that we get out of qubit codes. So in the case of our phase measurement, the syndrome that we get is a real number, and to the Fock measurements, of course, and the photon number measurements are integers, but we will not be doing them. And like I said, we're going to avoid doing these Fock-space displacements because they're very unphysical. So the trick is to steal an idea from CNIL and generalize this CNIL-style error correction to codes with rotation symmetry. And we're going to deal with error correction rather than fault tolerance. So our ancillary states that we use are going to be pure states. And the idea is we're going to use this teleportation circuit and consider propagating an arbitrary error through this circuit and seeing what a correction is. And so what happens here is we take a operator basis for the Hilbert space and look at how one of these errors propagates through the circuit. And it turns out that all we need to do is these two phase measurements. And then based on the outcome of these two phase measurements, we might have a possible outcome dependent Pauli, which we would then have to correct. The other thing to mention is that the gates that we're using in this circuit, especially CROT, have very nice properties that the errors don't amplify. They spread in a way that you can calculate. So I'm going to show you some numerics now that looks at performing error correction with this circuit and compares that to an optimal error correction procedure. And so here we're interested in the loss and dephasing channel. So this is energy relaxation, and then this is some sort of superposition or mixture of rotations in phase space. And the thing to note about these plots is that this kappa here, we take our master equation, we integrate it up to some time t, and kappa times t is like the noise strength. So if you think of a qubit channel, this would be kappa t is kind of like p for depolarizing. And so lower errors are on the left and higher errors are on the right. And then we're plotting the logical channel infidelity on the y-axis. And we've got two different codes here. This is this cat code and the binomial code. Now, of course, we want to see if our error correction is performing better than not doing anything. So in that case, we're going to compare it to this trivial encoding of the cavity. And this is reasonable because for loss errors, the higher you go up the Fock ladder, the stronger this sort of contribution from the annihilation operator, or if you want to think about the Krauss operators up there have a factor that goes like n. So when you do the trivial encoding and calculate the channel fidelity, you see that it's decreasing with the noise strength. So as the noise gets lower, the channel fidelity the channel infidelity is getting lower, which is good. And so this is our benchmark. We're only interested in when we do better than this. And so you can see here for the cat codes that generally below 10 to the -2, we're doing better. And as we increase the rotation symmetry, we're performing better and better. And we generically expect this to be true to a point, because at some point, as you increase the the rotation symmetry, you're making your wedges in phase space smaller and smaller. And this means that you might start to get, the dephasing errors might start to dominate, and you'll start to see a turnaround. The problem is it's difficult to do these numerics, so we haven't fully explored that. And then here's the same plot for binomial codes. You can see that the binomial codes are outperforming the cat codes. So now we compare this to this optimal recovery. So this is not using our explicit error correction circuit, but we solve a semi-definite program which determines the optimal recovery map to apply to the encoded qubit. And what's really surprising is that the explicit error correction circuit that we've given for this channel is performing very close to optimal. It's in some cases like half an order of magnitude off. And we really didn't do a lot to think about clever ways to decode and so on. So there's probably more wiggle room. And so I think this is pretty surprising. How long have we got, Chris? I think I'm starting to...
You have at least 10 more minutes.
Okay, okay. All right. Yeah, so this is pretty cool. I think this is the first example of an explicit error correction circuit for these rotation-symmetric codes. And we've found that it's pretty close to optimal. So there's many, many things to do. One of the things that we've been looking at recently is trying to optimize the inherent phase noise, or this phase uncertainty. And so this is essentially designing different primitives. And I won't go into too many details here, but the plot here, if you look at so these are amplitudes for plus X eigenstates. So these would be like the plus state for our error correcting codes. And I've gone and calculated the marginal phase distribution. And what's special about the states here is, according to the three of us, that these states have the minimal variance in the phase observable, or the phase variable. So that means the second moment here, say in this figure here, is as small as possible. And so we have been playing with this recently. So if I just show you some numerics that we have, we're not interested in loss in this case. We're just looking at the pure dephasing channel. And we found this curious thing that these other codes are ones that are well known. If you look at this sine code, it's called a sine code because these coefficients are essentially a sinusoid. The sine code has a lower channel infidelity for very large dephasing. So this is one of the first instances where a new code has outperformed these binomial codes, which is pretty cool. So then we had this idea that maybe we could start looking at a different channel, and I will just briefly explain it here. This channel is actually related to the dephasing channel. This is one way to write the dephasing channel. The dephasing channel is the case where this distribution here is a Gaussian centered around 0. And what we realized is that if you consider a code where you sort of displace that Gaussian to the left and displace it to the right, so now you have essentially a rotate left and a rotate right channel, which is, I've explicitly drawn the Krauss operators here for the simplest case, and rerun the numerics, we find that we can get a huge separation between codes that people know, like these Cat and Binomial codes, which are depicted up here, and these new phase optimized codes. So if you look, say, for example, at this point here, so what are we plotting here? This is channel infidelity on the y-axis. On the x-axis is the rotation angle as a percentage of the largest rotation you could do before you get a logical error. And for this n equals 2 code, that's pi on 2. So if you look here at rotations at about like 0.85, whatever that is, times pi on 2, we're seeing not for this, or maybe this one here, we're seeing 1, 2, 3, 4, 5, more than 5 orders of magnitude difference between the codes that have been known and the codes that we've designed. And so I think this illustrates one of the things that is really cool about bosonic codes at the moment is really simple ideas you can do can lead to dramatic improvements over what's known. Unfortunately, this is not a channel that anyone cares about, but it still illustrates that point. Okay, so in the last couple of minutes, I might just breeze through some updates and outlooks for the field in general. So I spoke a little bit about these translation codes at the start, these GKP codes, and I think there's been really two really cool results that have come out of actually Australia. This is work that Ben and Giacomo and Nick and Raf and Angela have done. So the first one shows that I guess something that I failed to mention at the start was that one of the reasons why people like these GKP codes is that all of the Clifford operations are done with Hamiltonians that are most quadratic in the annihilation and creation operator. And for bosonic systems, these are considered the free operations. And what's really cool in this paper that Ben's the first author on, they showed that the difficult part of GKP, which is making these magic states, or these cubic phase states or cubic phase gates, which is the sort of non-Gaussian or it's the thing that allows them to get universal computation, can be done with the vacuum state and heterodyne detection. And so this is a really cool result and is a bit of a game changer for CV codes. The second thing also from Giacomo, Ben, and Nick is these bosonic system subsystem codes. And I think that the name is maybe the name could be a bit different, but essentially what they're doing is they're taking, if you think of ordinarily you have a quantum operation and you can do a Steinspring dilation, enlarge the Hilbert space by including another system and represent the whole thing unitarily. The equivalent thing is a Naimark dilation for a larger system, a larger Hilbert space in the same system. So here you might imagine having a qubit and then enlarging the Hilbert space to a qudit or an oscillator, and then representing states and operators on that thing. And so what this paper does is it shows you how to take the continuous variable Hilbert space and decompose it as related to translation symmetric codes and decompose it into a qubit tensor some other stuff. And this has the potential to be a great simulation tool for bosonic codes. And this is because if you think of this error correction circuit that I showed you a few slides ago, if you have a Hilbert space of 160 for this first oscillator and 80 and I don't know 40 for this one, you can see that quickly the simulations become unwieldy and you have to do a lot of tricks in order to do this. But you might imagine using the kind of tricks developed here that you have a practical way to simulate these continuous variable systems. And I should say that this was for translation symmetry, and these guys are working on the case for the rotation-symmetric codes too. There's a bunch of big questions. I think one of the quests in qubit codes has just been to find the best code possible. So you might think that if you just ignore finding codes inspired by the symmetries of phase space, you might be able to find codes that are better than the ones we have. However, the gates might be unnatural. Another big question would be thinking about larger codes without concatenating them with a qubit codes, such as like a surface code or whatever qubit code you're interested in. There's a lot of questions to do with decoding. You don't, of course, this is going to be channel specific, but I think people really haven't thought about this. And then again, there's fault tolerance. In our paper, we covered some ideas that are leading towards fault tolerance, and other people have thought about this, but I think that it's not really done to the same level that people have been thinking about in the qubit literature. Okay, and this is my summary slide. So the new work that Anna, Ben, and I did was essentially unifying a bunch of old codes into a framework that lets us do error correction on any code that has a rotation symmetry. And we gave an explicit error correcting circuit that was close to optimal. I also showed you some preliminary results where by designing new code words, we were able to see 5 orders of magnitude improvement over the best known codes. So yeah, thanks for your attention. So enthusiastic.
Okay, is there any questions from our audience? If you have a question, just go ahead and unmute yourself and interrupt me. Okay, because I was going to ask a question myself, and it's about these Wigner functions. So you were showing us these Wigner functions.
These ones or earlier?
Yeah, these ones are fine.
Yeah. Okay.
So I guess like they can get quite complicated, right?
Yeah.
Like what is your impression of the utility of these? Like, do you find that it's useful to look at these, or is it just like a nice picture?
I just think they're a nice picture. I think there's very little that you can, I mean, okay, here we can see that these Wigner functions have, I mean, you could be fooled, but they have, you could say for sure they have an approximate symmetry, but you know, I can't tell you the entropy of the states by looking at the Wigner functions. In this case, I can tell you whether there's negativity because I know the normalization of the color map. But yeah, I think that more or less they're just pretty. I don't think there's actually, although as you well know, because you've worked on this, that the Wigner function itself is useful for saying things about whether things are efficient to simulate or not.
Yeah, I guess you can find some operational paradigm in which like negativity signals something, but right. Here, yeah, do you suspect that you'll need interference or you'll need negativity or anything like that?
I mean, absolutely. I mean, I think that you couldn't. I'm just trying to think. I actually haven't. I mean, I'm not sure you could make a code word. I don't think you could make a subspace that has only positive states. Although I don't know that for certain, because you'd need to. Here's a naive one: is you take superpositions of coherent states. Coherent states are positively represented, and then you get a Schrodinger cat code, and that has negativity.
I'm going to make a case for Wigner functions as opposed to the interpretive dance version,
Okay.
which is that actually experimentally what you often do is directly related to simple operations in your Wigner function phase space. And in fact, if you want to understand how to create many of these states, like looking at Fock state representations is going to do nothing for you. But if you look at the Wigner function, then you can get, you can actually work out, well, okay, if I do this series of controlled displacements and rotations and so forth in phase space, then I can create something that looks like that state. And that really represents very much, for example, the suite of gates available, for example, in these Yale experiments
right.
are literally, controlled or designed displacements and rotations in this Wigner function phase space.
Yeah, I think that's a fair point.
Can I ask, so all of the stuff that you've been talking about today, I think, is about how you encode qubits in these higher dimensional systems.
Yeah.
There, I believe, have been a couple of sort of preliminary results on how to encode oscillators in oscillator systems. For example, I think Yang Zhang has a nice result on that. Can you comment on how that may or may not relate to some of the sort of phase optimized codes or whatever that you've been talking about today?
Oh, that's interesting. Yeah, I mean, I've certainly seen these papers where they're encoding an oscillator into a collection of oscillators. I haven't looked at the specific encoding. My guess, and I don't know if Ben and Anna are still on the line, is that they're probably thinking about these translation-symmetric codes, or at least some variation of that. And I would guess that they haven't thought about encoding into these rotation-symmetric codes. I think if you did that, then going the next step and trying to figure out these, like the phase optimized versions of that would be, I would guess, relatively straightforward, but I don't know.
Because I think that that's actually something potentially interesting to do. You know, if you want to, in many physical systems that you might want to study, actually have oscillators in them naturally, and converting oscillators to qubits and then encoding qubits is a very, very unwieldy way to go. So if you want to build a computer that's going to be able to simulate systems that have oscillators in them, then being able to actually encode oscillators in these states is a really interesting possibility.
Yeah, I hadn't appreciated that. That is quite interesting. I mean, you might imagine that. So I guess you're saying, like, if you want to do simulation rather than computation, and you could then encode an oscillator and set up, you know, interactions so that you're simulating. Yeah, that's a really
right,
cool
exactly.
idea.
And I think, you know, one of the big arguments that people have said, oh, but you know, the problem with oscillators is that you'll never be able to make them error correctable. Well, I mean, you know, first of all, people have, actually all of this stuff shows that you can, well, certainly at least create error corrected qubits in oscillators.
Right.
And if you can start to create error corrected oscillators in oscillators, then you can start to potentially do some really interesting things, especially I think if you can combine the two and have qubits and oscillators in your systems.
And actually, this is kind of interesting because you might think that, you know, one of the arguments that's made against analog quantum computation is there's no analog classical computation. And I mean, I guess maybe one way of thinking about your point is that here's a way to actually protect and encode analog quantum computation.
Right.
Yeah. All right, that's a really cool idea.
Hi, Josh. The talk. I'm just wondering, you talked about using essentially magic states for doing T-gate, similar to like surface code or something. Do you still have some kind of mad overhead in distillation with that, or is it better or worse than you normally get through the surface code?
I personally have not looked at distillation. I think Anna may be looking at this with one of his graduate students. Yeah, I don't know how the overhead compares.
Okay, thanks.
Yeah. All right.
Okay, well, that's just about an hour, so good timing. Yeah, I think if we were in a room, you would hear a loud and amazing clapping for the wonderful performance you gave. So I guess I'll simulate that for you right now.
Oh, thanks, Chris.
Woo! Encore. All right. Thanks a lot, Josh.
Okay, thank you. Thanks for listening.
Bye.
See you, Josh. Have a good day.
Bye.